In this video, I'm going to talk about change point detection on a separable model for dynamic networks. My name is Yiklun K, and this is a joint work with Hangjian, Yanzhen Chen, and Oscar Hernan Madrid Padilla. To detect multiple change points in time series of network, we fit a time heterogeneous separable temporal exponential random graph model, while penalizing the sum of the Euclidean norm of the sequential parameter differences. Essentially, we impose a group Fils-Lassault regularization on the parameter, smoothing out minor variation and highlighting significant structural changes. We use the separable temporal ergon, which manage diet formation and dissolution separately to capture the structural change in network evolution realistically. Moreover, we demonstrate the capability of including nodal attributes to detect change points, and an R package is developed to implement the proposed method. For a node set N, let's denote Y, a 0, 1, n by n adjacency matrix as a network. The diet Yij in 0 and 1 indicates the absence or presence of a relation between node I and node J. The probabilistic formulation of an ergon for a network Y is the follows, where theta is a vector of parameter and g of y is a vector of network statistics, and the exponential of phi is the normalizing constant. As a surrogate, the logarithm of the pseudo-likelihood can be expressed as the follows, where delta G denotes the change in the network statistic when Yij changes from 0 to 1, while the rest of the network stays the same. Moreover, the Hangjian matrix of the negative pseudo-likelihood is positive semi-definite. So denote Yt as a network at a discrete time point t. Then given consecutive network Yt minus 1 and Yt, we can construct two intermediate networks, formation network Y plus and dissolution network Y minus as follows. And this table gives all four possible diet-wise transition and the corresponding construction of formation and dissolution networks. Posing that the underlying factors that result in edge formation are different from those that result in edge dissolution, Krivitsky and Hancock proposed the separable temporal ergon to dissect the evolution across network. Assuming Y plus is conditionally independent of Y minus given the previous network Yt minus 1, the separable temporal ergon for Yt conditioning on Yt minus 1 can be expressed as the product of two exponential family random graph model. As a surrogate, the logarithm of the pseudo-likelihood of a time heterogeneous separable temporal ergon is given by the following expression. In this work, for change point detection, this pseudo-likelihood is preferable for the following three reasons. First, the dyadic dependency in Y plus and Y minus is mitigated by conditioning on the previous network Yt minus 1. Second, large parameter shifts can still be reliably identified, even if the parameters are estimated by using a common approximation to the true likelihood. Finally, the pseudo-likelihood improves the scalability of the estimation procedure and permits efficient calculation. Now we are ready to define change point in terms of the model parameters. So we assume that the parameters in between two consecutive change points are all equals, while the change points or the parameters before and after a change point are not equals. So our goal here is to recover the collection of change point bk from a sequence of observed network YT where the number of change point K is also unknown. So to detect multiple change points, we propose the following estimator from a separable temporal ergo. Essentially, we want to maximize the log likelihood for the data while penalizing the sequential gap of the parameters. And the term D is a position-dependent weight. This figure gives an overview of the proposed framework. On the top, we have a sequence of observed network from Y1 to Y capital T. And then in the middle, we have the corresponding constructed network, the formation network Y plus, and dissolution network Y minus. And then at the bottom, we have a sequence of estimated parameters while we monitor the sequential difference between consecutive parameters. So to solve the problem in the original optimization problem, we first introduce a slack variable, and then we rewrite that problem as a constraint optimization problem. And let U be the scale do variable, then the augmented Lagrangian can be expressed as follows. We then make the change of variables where the gamma is the first slack variable and the betas collects all the sequential slack variable differences. Reversely, the original slack variable can also be collected by the following construction. And here we have the final expression for the augmented Lagrangian. Thus, we can implement the following ADMM procedure to update the parameters. So we recursively implement the 3 updates until certain convergence criteria is satisfied. So for the theta, we can implement a Newton-Raphson method to update the parameters. And then for the beta, we also have a Bloch-Coulomb descent method to update the beta, and then we also have a closed-form solution for the parameter gamma. So for the proposed ADMM procedure, we also have the ADMM convergence where the ADMM iterations go to infinity. We have the primal and dual residuals go to 0. Moreover, let's assume the restricted dual norm of the gradient satisfy the condition here, where the restricted dual norm is taken with respect to the total variation norm. And then if the estimation error satisfies a structural sparsity condition, then we have the mean square error satisfy the following estimation error bound. Once the parameters are estimated, we are now ready to localize the change point. So intuitively, the change point are the time points where the parameter at a time point t is substantially different from the parameter in the previous time point. So we can develop a data-driven threshold by first calculating the sequential parameter difference, and then we standardize the change in the parameter. And then we can construct a data-driven threshold, and we consider the time point with the parameter differences that is greater than this data-driven threshold as the change point that we want to detect it. Also, for our proposed framework, we have a hyperparameter lambda. So in this work, we use a BIC score to learn a set of zetas for each of the lambda, and then we choose the set of change point from the model with the lowest BIC score. And in this framework, we implement the proposed method on 2 real data. So the first real data is the MIT cell phone data, and then the proposed method can detect 5 meaningful change points here. So the largest spike corresponding to the winter break, which is a substantial event in the academic calendars that alternate the communication behavior among students. We are also able to detect the spring vacation as well as a sponsor meeting, where 2/3 of the students are meeting the project deadlines. We also implement the proposed method on the stock market data, where we detect 3 significant financial events, where the first one corresponding to the largest mortgage company filed for bankruptcy, and the second change point corresponding to the Lehman Brothers filed for bankruptcy, which is one of the largest investment bank in the US, and the third significant change point corresponding to the Dow Jones Industrial Average bottom. So our proposed methods, which estimate the parameter of the separable temporal ergon while penalizing the sequential differences in the parameter by using a group Fuse-Lassault regularization, is able to detect significant and meaningful change points from the real data. And this concludes our work for our separable model in detecting change points for dynamic graphs.